Currently, humanity has over 8,000 active satellites orbiting the Earth. These artifacts are a testament to the technological evolution of mankind. Producing a satellite and placing it into orbit can cost more than $500 million. But how is a satellite manufactured? To find out, let's go to the United States, the country that allocates the most money to satellite technology. The history of artificial satellite manufacturing began in 1957 when the Soviet Union launched Sputnik 1, the first artificial satellite to orbit the Earth. This event marked the start of the space race and demonstrated to the world that satellites were possible. Shortly after, in 1958, the United States launched Explorer 1, the first American satellite. Over the following decades, technology advanced rapidly, and satellites became more complex and specialized. In the 1960s, they began to be used for Earth observation, meteorology, and communication, in addition to military purposes. Over time, satellites became smaller, lighter, and more efficient, allowing their use in a variety of areas such as global navigation and environmental monitoring. Today, satellites are a key tool in our daily lives, aiding in communication, weather forecasting, navigation, and scientific research. So, what is the process for producing a satellite in factories? The manufacturing of communication satellites is a highly detailed and meticulous process that combines cutting-edge technology with advanced materials. The construction process is similar to that of an automobile, but with some key differences, as instead of starting with a sheet of steel, satellites are primarily built using lightweight and extremely durable materials, capable of withstanding the rigorous demands of the space environment. It all begins with selecting the most suitable materials, and among them, carbon fiber takes a central role. This material, although initially appearing soft, is woven into a strong structure and then combined with epoxy resin to harden it. The result is a material that is as lightweight as it is strong, ideal for the structural parts of the satellite. For example, antenna masts, which can be up to 6 meters long, are so light that they could be easily lifted with a finger. This lightweight property, combined with great strength, is crucial as satellites must endure the enormous forces of launch and the vacuum of space, where temperatures can vary between extremes. But carbon fiber isn't the only key material. Aluminum also plays an essential role, especially in the internal structures that support electronic components. This metal is known for being lightweight, corrosion-resistant, and highly efficient at dissipating heat, a vital property for the space environment, where temperatures can change drastically within minutes. The construction of the satellite progresses through several stages. First, the primary structure is created using carbon fiber as the base. To this initial structure, honeycomb panels are added, a design that combines efficiency and strength. These panels, which form the main framework of the satellite, may appear fragile at first glance, with a flexible and unstable appearance. However, this honeycomb core design conceals a clever trick. It is reinforced with aluminum or plastic plates on the top and bottom, and once the material dries, the frame becomes an incredibly rigid yet still lightweight structure. For parts that require greater strength and must withstand significant stresses, such as propulsion systems or solar panel supports, titanium is used. This material is stronger than aluminum, capable of withstanding extreme temperatures without deforming, making it ideal for components that face the highest demands during launch and in orbit. To protect the satellite's sensitive components from intense heat, materials like ceramics are used. This material can withstand high temperatures and is primarily employed in thermal insulation systems. Without these ceramic coatings, satellites could overheat due to solar radiation or the heat generated by the satellite itself. In addition to metals and ceramics, high-strength plastics and polymers are also used in flexible parts, such as cables or joints. These materials are lightweight and durable, helping to reduce the satellite's overall weight without compromising functionality. Plastics are also used for insulation, protecting internal systems from electromagnetic interference or physical damage. If the satellite has camera or telescope systems, high-quality optical materials like special glasses are incorporated, which must be extremely transparent and resistant to ensure efficient signal transmission or image capture without interference. Finally, The satellite's electronic components also require specific materials. Circuits and chips are manufactured using conductive metals like gold and copper to ensure efficient signal transmission. These components must be protected from radiation and extreme heat, so insulating and metallic materials are used to prevent damage during the satellite's time in orbit. Just like in devices such as phones and tablets, satellites' microchips are shrinking in size each year, allowing for greater efficiency and functionality in less space. These chips are grouped into blocks that are then assembled into the satellite's structure, progressively adding units and components until the final design is complete. As these materials are molded and assembled, the satellite begins to take shape. Each component is rigorously tested to ensure it can withstand launch and the extreme conditions of space, where there is no margin for error. Communication satellites are designed to operate in space for years, even decades, without the possibility of maintenance. There is no space workshop to fix failures. Therefore, before launch, each unit, component, and system undergoes a rigorous testing process designed to ensure their resilience and reliability in extreme conditions. These tests are essential to ensure the satellite fulfills its mission, regardless of the challenges it may face. One of the most critical tests is performed in thermal vacuum chambers, specially designed spaces that replicate the conditions of outer space. In these chambers, the satellite is subjected to extreme vacuum, completely removing air, and then faces temperatures ranging from -150 degrees Celsius to 150 degrees Celsius. This process ensures it can endure drastic temperature changes while orbiting the Earth. In addition to thermal tests, the satellite must pass vibration and acoustic tests that simulate the forces it will face during transport and launch. In a vibration platform, the satellite is subjected to shakes similar to those of a rocket's liftoff, while in an acoustic chamber, it is exposed to extreme sound levels akin to the deafening roar of rocket engines. These tests verify that the satellite's structure and internal components can withstand without damage. Antennas, essential for communication, also undergo detailed testing in anechoic chambers. This special space prevents signal reflection, allowing for precise performance evaluation. Due to the high radiation generated during the testing process, no one can remain in the room while the test is conducted. Only after passing these tests are the antennas fixed in their final positions, ready to operate once the satellite is in orbit. The final step in preparing the satellite is assembling the wings, which consist of the solar panels. With an average weight of over 1 ton, the satellite is transported to the launch site. Once the satellite arrives at the space station, the launch vehicle procedure begins, which starts with preparing the satellite, including again rigorous tests to verify that its systems are in perfect condition. Equipped with a payload adapter, the satellite is attached to this support using mechanisms designed to withstand the intense vibrations and forces of liftoff. Once secured, the satellite is encapsulated within the rocket's fairing, a protective structure that shields it from the adverse conditions of ascent, such as air resistance and potential contaminants. The encapsulated assembly is carefully transported to the launch vehicle, where it is integrated with millimeter precision to ensure the correct connection of its mechanical and electrical systems. After this integration, final tests are conducted to confirm that everything is in order and that the satellite will be properly released upon reaching its assigned orbit. The rocket or launch vehicle is typically built by companies like SpaceX, Arianespace, or the Russian Roscosmos. It must be powerful enough to overcome Earth's gravity. For example, SpaceX's Falcon 9 can carry payloads up to 22,800 kilograms to low Earth orbit and 8,300 kilograms to geostationary transfer orbit. The launch process involves several critical stages. First, the rocket is transported to the launch pad, an operation that requires specialized transportation systems. Then, fuel is loaded, such as refined kerosene and liquid oxygen, which will power the engines. During the countdown, final inspections are performed to confirm that everything is in order. Upon liftoff, the rocket traverses different layers of the atmosphere, discarding its lower stages once their fuel is depleted. This stage design allows the vehicle to reduce weight and gain speed efficiently. The upper stage, which contains the satellite, is responsible for positioning it into its designated orbit, whether a few hundred kilometers above the Earth in low Earth orbit or 35,700 kilometers in a geostationary orbit. Geostationary orbit is especially important for communication satellites, as it allows them to remain fixed over a specific point on Earth. This facilitates connection with ground stations and ensures stable signal transmissions for television, internet, and data. For example, geostationary satellites like those in the Intelsat constellation are responsible for a significant portion of global communication traffic. Once in orbit, satellites rely on solar panels to generate the energy they need to operate. They are also equipped with propulsion systems that allow for position adjustments. These adjustments are essential to counteract disturbances caused by factors such as the sun's and moon's gravity, atmospheric drag in low orbits, or solar wind. Modern satellites have a limited lifespan, typically ranging from 10 to 15 years, depending on the amount of fuel they have to maintain their orbit. When they reach the end of their operational life, they are deorbited, sending them into Earth's atmosphere for disintegration, or moved to a graveyard orbit, where they pose no threat to other satellites. And that's how an artificial satellite is built and placed into orbit. What did you think of the process? Let me know in the comments. If you enjoyed the video, click the like button and don't forget to subscribe to the channel. In the windows you'll see next, there are more videos that might catch your attention. Feel free to watch one. See you next time.